In this experiment, we followed experiment 14 in the Organic Chemistry Camosun College lab manual, and we just did the second part of the experiment, which was reducing nitrobenzene to aniline using tin and hydrochloric acid. So I just made a little flow chart following the steps, and it was quite long, so I cut it into 2 pages here. So for the first part, we weighed out 12.0 grams of solid tin, and then we added about 6.2 milliliters of nitrobenzene. From here, we used the pump to weigh out 30 milliliters of hydrochloric acid, and then we took a graduated cylinder and gradually added 5 milliliters at a time, and we were swirling it throughout this process. This reaction can become aggressive and does produce heat, so we actually had an ice bath ready to go. We added the 5 milliliter portions until the reaction was complete, and this was taking a while, so we ended up getting a hot plate and a stir bean and just letting it stir for us. The hot plate was actually off. Here's a close-up of the final 5 milliliter reaction. The next part of the experiment was to steam for about 20 minutes, but because we already had the hot plate, we just set the temperature to 3, and then we had the stir bean to stir for us. It was just a little bit faster. While the reaction was steaming and heating away, we measured out 100 milliliters of sodium hydroxide and then 25 milliliters of water. The reaction had to cool as well to room temperature before we could add the sodium hydroxide and water, so we were also just greasing the tubes for the next part of the experiment. The solution was nice and cool, so we added the 25 mils of water and then followed with the 100 milliliters of sodium hydroxide. This reaction looked kind of cool. It produced like some white chunks. The next part was to test the solution to see if it was alkaline, and if it wasn't, we would have to add more, but because we added so much, it seemed like it would be, and sure enough, we tested and the strip was blue. Moving on to the second part of the flowchart, we transferred this solution carefully to a beaker just to try and get as much solution without chunks, and then further transfer this to a 250 milliliter distilling flask, which is like the round ones. Here is the longest part of the experiment, and it is waiting for 50 milliliters to distill. We have multiple different angles of this process, different time lapses, and I was watching it at the beginning and was quite concerned because I could see vapor coming out of the tube, and then we realized there was no water. We forgot to turn the water on, and the purpose of the water is basically to cool the vapor droplets and condense them so they can collect on the edges of the tube and then drop into whatever glassware is collecting the droplets. If the collected distillate was yellow, we were to add some decolorizing carbon, and this would clear up the solution, but ours was quite clear to begin with, so we got to skip this step. Here is a real-time close-up of some condensing distillate into the glassware. We then added 4.0 milliliters of hydrochloric acid and heated the solution to 50 degrees Celsius. I ran to the fume hood with it because it produced some vapors and I didn't know what that was. The solution was heated to 50 degrees Celsius on a hot plate. We had a thermometer to check, and then while this was heating up, we weighed out 9.0 grams of sodium acetate. So our distillate with the hydrochloric acid is straight off the hot plate, and here we have all the other reagents ready to add. So we're adding first 7.5 mils acetic anhydride. Then comes the solid 9.0 grams sodium acetate, and immediately the 25 milliliters of water. And we swirl this to mix everything, and the next step is to cool it. Ice bath! So it's in the ice bath. And the final step is to filter the crystals. So we have a Hirsch funnel and vacuum filtration setup. Here we're pouring the crystals in, and we just wash the rest out of the beaker using some ice cold water. After the crystals vacuumed out most of the moisture, we pressed the crystals on filter paper to dry them out a little bit more, and then took a weight. The weight was about 2.22, but then it changed. The next step was a melting point, so we just have the melt point apparatus and use the tiniest bit possible, and then we recorded that melting point as well. For the IR spectroscopy component of this experiment, we take the tiniest amount of product and then potassium bromide, and they're both white powders or crystals, and then we add them to a mortar and pestle, and you want to emulsify this for at least 3 minutes. Once the mixture is fully emulsified, you're going to add the powder just enough to cover the surface of a bolt. You want just enough to cover all the edges, but not too much, and then you're going to put the other bolt in, and we're going to pop all of this into a vise, and you're going to tighten that really tight because we want to make a solid KBR plate, and we don't want it too thick or too thin as we need infrared light to pass through. Unfortunately, ours is cracked. It looks kind of cool, but this didn't affect the AIR. The infrared light was still able to pass through and it wasn't too thick. Here we are running the background test, and then here we are with our sample running the IR. The results from the IR test show the amide, which has an N to H group, and that's shown on the left here with the peak, and there's also a double bond to the O in the amide part. That's also shown on the spectroscopy graph, and then we compared these results to an uncredited source from the internet, and they are very similar. Therefore, we did create pure acetanilide. Our Camosun College campus is located on the traditional territories of the Lakwadan and Wasanich peoples. I would like to acknowledge and thank their graciousness for us to use their territory.